Hello, in this video we'll be looking at particles moving along a line, and this is in relation to IGCSE differentiation questions. We'll be looking at how to model the movement, demonstrate the graphs of displacement, velocity and acceleration and see how they change over time. Look at how to find the formula for velocity and acceleration, and I'll do a model answer for an exam style question. So first of all, you'll be given a question which will talk about a particle, and it'll be moving along a line in relation to a point. Normally the point is 0 where we begin, and you can look at it like this in terms of a numbered line, and you have a point here represented by the green dot, and it might move this way and then it might go back this way. It might oscillate between the two, or it might just go this way and then back this way, or it might go this way and then that way. But it's moving backwards, and they'll generally do it so it goes one way and then it will stop and then it will go back. Now clearly, as it's moving through time, when we get to a certain point and we turn again, you've got to say, well, what happens? We want to know what happens at that point, or when is that point reached, in what time. Now, a couple of things to notice. We have distances that are positive from 0 and negative from 0. So moving my green dot, if I go this way, I'm going towards the positive numbers on the number line, so I'm going a positive distance from O. And if I'm going this way, it's a negative distance from O. In terms of velocity, now velocity is just speed, but with direction. So we can have a positive velocity going this way, a negative velocity going this way. Please note that even if I'm over here, as soon as I start moving this direction, it's a negative velocity. Even though I'm in the positive numbers here, it's a negative velocity because of the direction that I'm traveling in. Now this interactive I've actually taken from GeoGebra. I would highly recommend you visit this particular one. The web address is at the top here. And also just explore GeoGebra anyway, especially when you're looking at graphs and functions. It's a really good way of trying to see exactly what happens when you change different elements of a function. And for this, it's going to be really good for showing the different graphs for speed, or sort of for distance, velocity and acceleration. Now we have a particle here on the left-hand side here, and it will go up and down. My demonstration previously, we had the number line going horizontally, which is the way you would normally see it. So just think about that line and then it now going up and down rather than going across. The axis going across it is time. Time in mathematics, we always have it going across on the horizontal. And this is just showing the position of the particle. Let's have a look at the particle moving first of all, just to see what happens. So I'm going to start the time now, and you see the particle going down. So initially with this one, it goes down, and then it goes, so it's going away from 0, and then it's going back through towards 0, and then it's going up into the positives. Now I'll just show that one more time, just so you get an idea of what's happening. If I just reset that. So the particle, when time starts, goes into the negatives. So that's the blue square. It's slowing down now, and then it's changed direction, so it's speeding up and it's accelerating and it's going away and away. And as far as we know, it goes all the way into the positives towards infinity. The function for this, you can see on the left-hand side, the function is called s of t, although it's actually written as 5x cubed minus 5x squared. So this is showing the particle moving. We have a particle that goes basically into the negatives from 0, stops at some point, turns around and instantaneously accelerates towards the positive numbers. But what does the velocity graph look like? So let's have a look. So the velocity is the speed. So I can click it on, in fact, let's just look at the distance, sorry. Let's do the distance first. So I've got the distance graph. The distance graph looks like this. So if I reset this, as you'll see the particle moving, you'll see the distance away. So the distance goes down because the distance is negative, and then the distance gets closer and closer and closer and closer, and then it goes away again into the positives. So what we have here is, as this graph just shows how far away from O we are. We're negative distance away. Get to some point around about negative 0.75, and then we're going all the way through. And as you can see here, that when t is equal to 1, our particle is back where it began. Pretty tricky to do this on the iPad, but you, again, I say have a little play with this activity yourself. but when a particle is at time 1, it's in exactly the same place it started, and then it goes further away. So that's the distance. S is used for distance for most of these types of diagrams. So let's have a look at the velocity. So the velocity is this graph. So have a look at what happens with the velocity now. That's the speed, but speed obviously with direction. So let's go start. And as you can see, the velocity is changing all the way through. It's never constant. Let's go back through that again. And what we have here is it's speeding up, but in a negative direction. Now it's slowing down. And then it just carries on accelerating. It carries on getting bigger and bigger. So let's just slow this down and go through step by step. So as our particle moves, it starts speeding up. It's at negative speed, and then the graph gets to around about this point here, and then we have a change. So it slows down. You can tell it's slowing down because the gradient is getting less, and then at some point it just turns around, and then it starts from here, speeding up and up and up, and getting further and getting larger and larger as we go. So if we look at the two graphs together, they do kind of make similar shapes, but they're not identical. The curves are different. So you want to make sure you don't confuse the two curves. Let's see the two together with the particle moving. And when you're studying this one, have a look at what it says on the left-hand side. You have direction and speeding up, so it's telling you what is happening to the function. Let's do this one more time. So the direction is down and it's speeding up. No, the direction is up and it's speeding up. Okay. Now the acceleration one is more tricky to show on this graph because of the scale that we're using. The acceleration one looks like this. If I can zoom out, it's a straight line. Straight line, not an interesting graph. Now we're not expected to draw the graphs on this, but it's useful to see what happens with all these three. We'll do one example showing all three together. Reset this. Very difficult to get your head around exactly what is going on there, I think, looking at all three together. Not recommended, but if you want to have a little play with this, please do. It hopefully gives you an idea of what the graphs kind of look like. They are three separate graphs. They're interlinked, but they are separate. One is for distance, one is for velocity, and one is for acceleration. Now, in the exam, you'll be using differentiation to change a function or a formula. So we're going from displacement, which is like a distance, velocity, which is speed with direction, and acceleration. And the way you do it is this. If you want to go from a distance graph to a velocity graph, you're changing distance against time. So that means you are going to have the velocity. So we differentiate. So if we start with S here, then we do ds by dt. We differentiate our distance by time, and we get our velocity, or our speed, you could call it. But I think velocity is the one you want to use because it has direction. Acceleration is just a change of speed or a change of velocity against time. So we differentiate it again. In this case, we would do dv by dt. There is a way of doing it. You'll see this during A-level studies when we actually do, we differentiate once and then we differentiate again. So we will do d2s by dt squared. It's a different notation. If you see that on the internet, don't worry. It's the same sort of thing. But for what we're looking at GCSE, we just differentiate once to get speed or velocity, differentiate again to get acceleration. This graphic is taken from the mmerevise.co.uk. It's a really nice little graphic. It's a really good website, and this web page at the bottom here will also give you some different ways of looking at what they call kinematics. Kinematics is just the mathematics of moving points. It's a mechanics style phraseology that we use. So finally, here's a question. And it tells us that we have a particle P moving along a straight line that passes through a fixed point O. So this is basically what we looked at the beginning, just a point moving along a line. Okay, they give us a displacement, and very often in the GCSE, it'll be a cubic expression. That's what this one is. The one in the interactive was a cubic as well. This one is 4t cubed minus 27t plus 8, and t obviously is time, and time is greater than or equal to 0 because we don't really have negative time. That is going to mess everything up if we start with doing time being a negative. It says the direction of the p reverses when p is at a point A. So p is going along a line. I'll do a little sketch of this. We've got O, and we have our point P, and at some point P will go along this line here, and at some point it'll turn around and it'll go back the other way. So this point we're looking at here is point A. So it says the direction of motion P reverses when P is at A. So P goes this way, gets to A, and then instantly reverses. So it's exactly the same as the interactive we've seen. It says that the acceleration P at the point A, the acceleration of P at the instant when P is at A is little a meters squared, meters per second squared, sorry. So find the value of A. So we're looking at this and going, okay, it says acceleration. Now clearly that's going to be differentiation twice, because if we differentiate this, we get the speed. So let's look at what we can do with this question. Let's take our function. And we know that our velocity is going to be equal to our dx by dt. We're changing our distance here against time. So if we differentiate our function, which is 4t cubed, 4t cubed goes to 12t squared. The 3 comes down to multiply the 4, and we take 1 off the 3. The minus 27t just goes to minus 27. The t will disappear, and the 8 is no longer there. 8 differentiates to nothing. So we have a function now for our velocity, 12t squared minus 12t. So that's the speed. Now remember, when our point is going along here, when it gets to point A and it turns around, at that instant, its velocity is 0. So we can find out the time of this, because we can say, well, this is our velocity. So what happens, at what time is the velocity 0? So we can say that 0 is equal to 12t squared minus 27. Why did I write 2t there? Let's go back and change that. Okay, should have spotted that. Okay, so we make that equal to 0. So now we just got to solve this function here, or this equation. So I've got 27 equals 12t squared. T squared is 27 over 12. 27 over 12 is 9 over 4. So we can say that t squared, it's a bit smaller, t is equal to the square root of 9 over 4, which is equal to 3 over 2. Now technically it's plus or minus 3 over 2, but we're dealing with time, and time cannot be negative. It even reminds us that in the question. So we could ignore that, and we just say that t is 3 over 2, or 1.5 seconds. Okay, so the time is 3 over 2, or t is 1.5 seconds, and that's the point when our particle stops and goes backwards. So that's when we get to point A. So the time is there. Now the question asks for the acceleration. It wants the value of A, the acceleration at point A. So for the acceleration, I know what time it happens, but I don't know the formula for acceleration. But acceleration is just going to be the differentiation again, this time of the velocity. So my acceleration is going to be dv by dt. So I differentiate my velocity. So I'm differentiating this thing. That will come out quite nicely, because 12t squared goes to 24t, and the minus 27 disappears. So that's my formula for the acceleration. I now want to say, well, what happens when t is 1.5? What is the acceleration? So when t equals 1.5, the acceleration is 24 multiplied by 1.5, which is 36 meters per second squared.